We're going to start our unit on exponential growth and decay. We've been talking about exponents and how to add, subtract, multiply, and divide them. We've also talked about radicals. So what we're going to do is we're going to learn how to write an exponential equation, which we looked at graphs of exponential equations way at the beginning of the year. The thing to remember about exponents is that they're either going to increase or decrease really, really fast, because it is exponential. So we're going to look at this situation here. The National Association of Realtors estimates on average the price of a house doubles every 10 years. Tony's grandparents bought a house in 1960 for $10,000. Assume the trend identified by the National Association of Realtors applies to Tony's grandparents' house. What was the value in 1970 and in 1980? Well, if it doubles every 10 years, and in 1960 it was $10,000, then in 1970 it's going to double, it's going to be $20,000. And then in 1980, that $20,000 is going to double, and now it's $40,000. What is the difference from 60 to 70? Well, 10,000. And the ratio of 70 to 60, and remember ratios, we can write, this is from 6th grade, we can write it as a fraction, right? We can use a colon, or we can use the word 2, and of course we're going to be using a fraction, right? A compared to B, A colon B, A to B. And order matters. So 1970 is first, for this is going to be your numerator. So the value in 1970 was 20,000 over the value in 1960 was 10,000. So that means that we can simplify that to 2. Actually, I'm going to simplify it this way. So when we complete the table here from 1960 to 2010, we're going to see a pattern emerging. So here we go. Decades since 1960. 1970 would be 1, and then 2, 3, 4, and 5. The value of house, and remember, it's going to double every 10 years. So this is 20,000, 40,000, 80,000, 160,000, and 320,000. So then it wants the differences between the decades. Okay, well, from 10 to 20 is a difference of 10. From 20 to 40 is a difference of 20. 40 to 80 is a difference of 40. 80 to 160 is 80. And then 160. So then we're going to write that ratio that we talked about of the consecutive decades. So we already did this a minute ago, where we had 20,000 over 10,000, which simplifies to 2. So if we do the next one, it's going to be the 40,000 compared to the 20,000, which again reduces to 2. And you should see a pattern here of, then we have the 80,000 compared to the 40,000. So it's the next decade compared to the current. Again, 2, 160, and 80 is going to be 2, and then 320 over 160 is again 2. And that 2 pattern is going to be important. It says, what patterns do you recognize in the table? Well, 1, it is exponential, because it increases by a factor of 2. And when we graph it, we're going to see that the graph will curve. Okay, so it's kind of like our geometric sequence, which was also exponential. Next page gives us a little more practice with this. It says, write the house value as a sequence. Again, geometric sequence. We just talked about this. And identify the sequence as arithmetic or geometric. It's going to be geometric because we were multiplying each time. So if we're going to write this as a sequence, right, we always start with 1. So we're not going to, so we're going to say, actually we're going to start with 1. So it's going to be 20. Unless we say 160. But we can start with 20 and then 40. 80, 160, and we could put thousands. And our geometric ratio is going to be 2. So using the data from the table, graph, and we're going to see what happens. So again, pay attention to your units. The decades since 1960 is going by ones, but the value of the house is increasing by 10,000s. So in 1960, which we're going to say is decade 0, it was 10,000. And then in 1970, which was 1 decade since 1960, would be 20,000. I'm going to change to a highlighter here. And then we have in 1980, which is 2 decades, it jumped to 40. 3 would be 1990, so 40 times 2 we said was 80. And then 80 times 2 would be 160. And then 5 was all the way up here to 320. Now, we can connect the dots, and the reason we can do that is we can say that this is continuous in the sense that we could find the value in between those decades. Okay? Number 8 says, the data comparing the number of decades since 1960 and value of the house are not linear. Explain why using the table and the graph. So it is not linear because there is a common ratio instead of a common difference in the table. And we can say that the graph is curved, not linear. Using the information that you have regarding the house value, predict the value in 2020 and explain your prediction. So you can do a couple of things here. You can go back to your table. We went to 2010 and we said that it was 320. And we can just double that for 2020 to 640. Or you could go ahead, you could even figure out 2020, how many decades from 1960 that is, and you could do it that way. Extending the table since we have the previous one is probably easier. Tony would like to know the value of the house in 2005 using the same data. Predict that value and explain how you made your prediction. So you need to think about this. So we know, I'm going to write it. In 2000, the value of the house was $160,000. And then in 2010, the value was $320,000. So in 2005, we're kind of looking for a middle ground there, right? So we could find we can do this a couple ways. We can average, we can say 160 plus 320 divided by 2, which is actually the same as, let's see, what would we get there? 480 divided by 2 is 240,000. We can do it that way. We could say 160 times a decade and a half, which is also 240,000. We could say 160 plus 160 divided by 2, which is also 240,000. So lots of ways you could find it. Really, they're all the same. The increase in house value for Tony's grandparents is an example of exponential growth. And we can model that with an exponential function. Okay, so this is how you write an exponential equation. F of x is equal to a times b to the x power. Okay, where a is your start value, like our b on our y equals mx plus b, and b is your common ratio. We're going to practice writing some equations with that today. In exponential growth, quantity is multiplied by a constant factor greater than 1 during a time period. So if it's growing, that means our b value is more than 1. So I'm just going to write that equation over here for us again. F of x is equal to a b to the x power, where a is our beginning. It's essentially our y-intercept, which I know is confusing because we're used for it to be our b value. We can also call it our initial. And b is that common ratio. So the value of the house grew exponentially because multiplied by a constant factor. What was the constant factor? It was 2. Function that can be used to model the house is 10,000 because this was our initial value, times 2 to the t power, where b, which is our common ratio, is 2. So what is the meaning of h of t, and what are reasonable domain and range? So h of t is the value of the house. So your domain, and you can go back to your table or you can go back to your graph, is, if we go, let me zoom back out. So if we go to our graph, our domain is x's, so we can see it's 0 on. So we can say t is greater than or equal to 0 because it was 0 initially for our 0 decades since 1960. The range, though, started at 10,000 and went up. So our range, we can say h of t, because that's what they give us instead of y, is greater than or equal to 10,000. How is it related to the function? For number 11, we can say 2 was our constant factor. We can also call it the common ratio. Complete the table for function h of t. All right, well, we started with 1. You can also start with 0, so for 0 you would have 10,000. It's the same exact table we had previously, 20, where we had that constant factor of 2, so it's just doubling each time. Now, I want you to notice the notation here. 1 times 10 to the 5th. 10 to the 5th is going to be 10,000. I'm sorry, it's not 10,000. It's 100,000, if I remember right. 1, 2, 3, 4, 5, yeah. 1, 2, 3, 4, 5. Yeah, it's 100,000. So we're going to actually have to start way down here. For it's really small, and we don't get to 160,000 until 4 years. So we're actually, about here. We're close to 100,000 at 3. So it's just going to and go up like that. All right, so what was the value in 1960? It was 10,000. Calculate the value in 2020, and how does the value compare to your prediction? They want us to actually use the calculator, so we're going to actually do, or not in 2020. We're going to use the calculator on 17. In 2020, we said that it was 640. So we're going to do 17 in class tomorrow. And then we're going to do some practice problems that we'll probably take for a grade. Have a good night.